Humanity stands on the verge of becoming an interstellar species. This future depends entirely on 25 breakthrough propulsion concepts that shatter the limits of known physics. By the end of our journey, you will understand the real science that could power our voyage to the stars. We will uncover how a spacecraft might ride a wave of warped spacetime, and how a star could be fueled by the emptiness of the quantum vacuum. What do you believe is the ultimate destiny for humankind among the cosmos? That dream of sailing between suns felt utterly impossible for generations, a beautiful fantasy penned by storytellers gazing through telescopes. The cold mathematics of spaceflight delivered a harsh reality. Even our most powerful chemical rockets, the very engines that took us to the moon, are pathetically inadequate for such a journey. A trip to our nearest stellar neighbor, Proxima Centauri, would take tens of thousands of years with today's technology. You would need a spacecraft capable of carrying generations of crew, a veritable ark drifting through the blackness for longer than recorded human history. This immense gulf of space and time is the fundamental obstacle, the great silence that has kept us isolated on our pale blue dot. But what if the problem isn't the distance itself, but how we choose to cross it? The true breakthrough lies not in building faster rockets, but in rethinking the very nature of the journey. This shift in perspective begins with a theoretical foundation that sounds like magic, yet is rooted in the firm bedrock of Einstein's physics. It starts with a simple, profound question. What if we could take a shortcut? Our fastest spacecraft are cosmic snails in the grand arena of the galaxy. The Parker Solar Probe, for instance, achieves breathtaking speeds within our solar system, yet it would still require thousands upon thousands of years to reach our nearest stellar neighbor. This is not a failure of engineering, but a direct consequence of two unyielding laws of physics. The first is known as the tyranny of the rocket equation. It is a simple, brutal mathematical reality. To go faster, you need more fuel, but that extra fuel adds more mass, which then requires even more fuel to push that increased mass. This creates a vicious cycle of diminishing returns, where each tiny gain in speed demands an exponentially larger and more massive fuel tank. To reach even a fraction of light speed with a conventional rocket, you would need a spacecraft almost entirely composed of fuel, a flying gas canister with virtually no room for a payload or crew. It is a fundamental dead end for interstellar travel. The second barrier is even more absolute. Einstein's theory of relativity established the speed of light as the universe's ultimate speed limit. Nothing with mass can ever reach or exceed this velocity. It is not an engineering challenge to be overcome with better materials, but a foundational rule woven into the fabric of reality itself. So we are left trapped, caught between an equation that demands the impossible and a cosmic law that forbids the necessary. This is precisely why the old ways of thinking will never get us to the stars. The coming concepts are not mere improvements, they are rebellions. They are attempts to find a loophole in the rocket equation, a backdoor through relativity, or a way to rewrite the rules of the game entirely. Our journey begins with a concept that takes this last approach most literally, by manipulating the very stage on which the universe is set. Such a craft would not push itself through the cosmos, but would command the cosmos to move for it. The Alcubierre warp drive proposes a vessel that contracts the very space in front of it while expanding the space behind, surfing a wave of distorted spacetime. Picture yourself on a moving walkway at an airport. You are standing still relative to the walkway itself, yet you are propelled forward as the ground beneath you shifts. The warp drive operates on a cosmic scale, creating a similar effect. the spacecraft sits comfortably inside a stable pocket of normal spacetime, a protective warp bubble, while the fabric of the universe itself does the strenuous work of motion. This elegant loophole means that nothing within the bubble is accelerating locally, thus never violating Einstein's universal speed limit. The ship itself is motionless within its own little pocket of reality, even as the bubble carrying it moves faster than light. The engine required to create this warp bubble, however, relies on something truly strange, a form of exotic matter that generates negative energy density. Think of it as a kind of anti-gravity, a substance that pushes space apart rather than pulling it together. While the existence of such matter is still purely theoretical, and the initial energy calculations were mind-bogglingly vast, recent scientific papers have explored ways to drastically reduce those requirements. What was once a fantastical equation on a blackboard is now a subject of serious, if highly speculative, research in labs around the world. The warp drive represents the ultimate ambition of propulsion physics, not to build a faster engine, but to conquer distance itself by manipulating the stage upon which we all exist. This pursuit of manipulating fundamental forces leads us directly to another concept that draws power from the very void of space. Harnessing the universe's most potent fuel requires confronting its most volatile substance. Antimatter is the ultimate cosmic opposite, a mirror image of the particles that make up our everyday world. When matter and antimatter meet, they vanish in a flash of pure energy, a total conversion of mass into power as described by Einstein's iconic equation. This is not merely efficient combustion, it is the complete and utter dissolution of substance into force. An antimatter rocket would capture this phenomenal release, directing the torrent of high-energy particles created by the annihilation through a magnetic nozzle to generate immense thrust. The efficiency of such a system, measured as specific impulse, would be thousands of times greater than the best chemical rockets we have today. A journey to Mars could be reduced to weeks instead of months, and voyages to the outer planets would become routine expeditions. For interstellar travel, this represents a brute force solution to the rocket equation, a way to pack the energy of a stellar explosion into a manageable fuel tank, potentially accelerating a vessel to a significant fraction of light speed. Yet, this incredible power comes with monumental challenges. We can only produce antimatter in infinitesimal amounts within massive particle accelerators, and the cost to create a single gram would dwarf the entire global economy. Storing it is another nightmare, as it must be suspended in a perfect vacuum within powerful magnetic fields, never allowed to touch the walls of its container. A single mishap would trigger a catastrophic explosion, and then there is the intense radiation produced by the annihilation process, which would require sophisticated shielding to protect any crew. This is a technology of extremes, offering the keys to the solar system in exchange for mastering a force of pure destruction. But what if the ultimate engine requires no fuel tank at all? This elegant vision of a ship feeding on the galaxy itself confronts a universe far emptier than it first appears. The Bussard Ramjet proposes a vessel that is both engine and organism, a cosmic whale swimming through the sea of space. Instead of carrying its immense fuel supply from the start, the ship would extend a vast, invisible net. A magnetic field stretching hundreds of kilometers wide would act as an electromagnetic funnel, sweeping up the individual protons of hydrogen that drift through the interstellar void. These particles would be guided into a fusion reactor at the heart of the ship, where they would be crushed together to form helium, releasing the same kind of energy that powers stars. This continuous process would, in theory, generate constant thrust, allowing the ship to accelerate for years, even decades, potentially reaching a staggering fraction of light speed. It is the ultimate expression of living off the land, turning the very emptiness of space into a highway. Yet the interstellar medium is not a dense ocean, but an incredible vacuum, far emptier than any we can create on Earth. The magnetic scoop would need to be phenomenally large and efficient to collect enough fuel. More critically, fusing plain hydrogen nuclei, a process known as proton-proton fusion, is extraordinarily difficult. It is the same slow, sluggish reaction that sustains our Sun over billions of years, not the rapid, energetic process you would need to power a Starship engine. At lower speeds, the drag force from colliding with this sparse hydrogen would actually counteract the tiny amount of thrust being generated, creating a speed limit below which the ramjet simply cannot work. The dream is one of self-sufficient grace, but the reality is a gauntlet of engineering and physics that we are only beginning to comprehend. If harvesting fuel from the moving galaxy proves so challenging, perhaps the answer is to draw power from a stationary beacon of unimaginable intensity. The sheer brilliance of this idea lies in its elegant simplicity. A spacecraft sheds its greatest burden, the fuel, and instead rides a river of pure light. This is the promise of the laser sail, a concept that transforms a beam of photons into a cosmic wind. Picture a vast, silvery sheet, thinner than a soap bubble and stretching for meters, even kilometers across. This is the light sail, and it requires no internal engine. Its only fuel is the gentle, persistent pressure of light itself. While sunlight provides a faint, constant push, the true potential is unlocked by a colossal laser array stationed in orbit around Earth or the Sun. This artificial star would focus a beam of unimaginable power onto the distant sail, bathing it in a continuous torrent of photons. Each photon imparts a tiny amount of momentum, and collectively, this relentless push could accelerate a lightweight probe to a significant fraction of light speed over time. The Breakthrough Starshot initiative is a bold plan to do exactly this, aiming to send gram-scale nanocraft to Alpha Centauri within a single generation. These would be like intelligent interstellar grains of sand propelled by the light of a human-made star, yet the path of the light rider is fraught with peril. The laser array required would demand power on a global scale, a monumental engineering feat in itself. The sail must be perfectly reflective and strong enough to survive an acceleration that would rip conventional materials apart, all while navigating a minefield of interstellar dust grains that, at such velocities, would hit with the force of a bomb. And perhaps the greatest challenge of all is the destination, for the laser push only works one way. How do you slow down when you are moving too fast to carry brakes? The laser sail redefines the very philosophy of a vessel, separating the source of propulsion from the traveler entirely. It suggests a future where we launch not just ships, but the very highways they travel upon. This logic of external power leads to an even more visceral concept, one that harnesses the fury of controlled stellar explosions. There is a strange kind of audacity in a propulsion system that uses bombs as its fuel. Project Orion was not science fiction, but a deeply researched and shockingly practical concept born in the 1950s and 60s. Its principle was brutally simple. A spacecraft would eject small nuclear bombs out the back at a steady rhythm. These devices would detonate a short distance away, and the resulting plasma fireball would slam into a massive, armored pusher plate attached to the ship's stern. Each explosion would be a hammer blow, transferring its immense momentum through the plate and pushing the vessel forward. To prevent the crew from being turned to jelly by this violent, rhythmic pounding, a sophisticated system of shock absorbers would smooth the pulses into a continuous, powerful acceleration. The numbers were staggering. A full-scale Orion vessel could theoretically reach several % of the speed of light. transforming our entire solar system from a collection of distant worlds into a manageable neighborhood. A trip to Saturn and back could become a matter of years, not decades. The dream of true interplanetary civilization was within our grasp using technology we already possessed. The downfall of Orion was not a failure of physics, but of politics and public sentiment. The idea of repeatedly detonating nuclear weapons in Earth's atmosphere to achieve orbit was understandably terrifying, raising legitimate fears of radioactive fallout and global proliferation. Yet in the pristine vacuum of deep space, untainted by geopolitical concerns, Orion remains one of the most potent and fully realized propulsion concepts ever put to paper. It represents a path not taken, a testament to a moment when we considered using our most powerful creations not for destruction, but for a grand exodus to the stars. This raw, explosive power, however, gives way to a more elegant and controlled application of the atom. While the raw power of Orion was immense, its controlled cousin offers a more immediate and practical path forward. Nuclear thermal propulsion is not about explosions, but about intense, focused heat. Imagine a rocket engine where the fiery combustion of chemical fuels is replaced by the searing energy of a miniature star. A compact nuclear fission reactor, no larger than a trash can, sits at the heart of the engine. Liquid hydrogen, stored at frigid temperatures, is pumped through the reactor's blazing core. In an instant, the supercooled propellant is flash-heated to thousands of degrees, transforming into an incandescent plasma that violently expands and blasts out of the nozzle at tremendous speed. This is the principle of the nuclear thermal rocket. It trades the brief, intense burn of chemical engines for a far more efficient and sustained push. The key metric here is specific impulse, a measure of engine efficiency. The best chemical rockets top out at around 450 seconds. A nuclear thermal engine can achieve nearly 900, effectively doubling the performance. This translates directly into shorter journey times and heavier payloads. A crewed mission to Mars, for instance, could see its transit time cut from 9 months down to just 5 or 6, dramatically reducing the crew's exposure to cosmic radiation and the psychological strain of deep space. The technology is not just a theory. It was tested and proven on the ground here on Earth during projects like NERVA in the 1960s and 70s, where engineers successfully built and fired operational engines. The reason none ever flew was a shift in political priorities, not a failure of the science. Today, that legacy is being revived. Modern initiatives like the Draco program are actively developing new designs for a demonstration in space. Nuclear thermal propulsion represents the most plausible next step, a powerful workhorse engine that could open up the inner solar system for routine travel and establish a permanent human presence from the moon to the asteroid belt. It is the indispensable bridge we must cross, a testament to applying a formidable power with precise control before we can ever hope to reach for the stars. That very same nuclear fire, when applied not just for heat but for pure, unadulterated power, unlocks an even more capable system for the void. The next step in our journey moves from splitting atoms to fusing them together, unlocking the very process that gives stars their light. A nuclear fusion rocket seeks to bottle a miniature star and use its radiant fury for thrust. Inside a magnetic chamber, isotopes of hydrogen, like deuterium and tritium, are heated to temperatures exceeding 100 million degrees. At this infernal heat, atomic nuclei overcome their natural repulsion and fuse together, creating helium and releasing a torrent of energy. This creates a superheated plasma, an electrically charged gas far hotter than the surface of the sun. Instead of simply using this heat, a fusion rocket channels this incandescent fury, directing the expanding plasma out of a magnetic nozzle to generate thrust. The exhaust velocity would be an order of magnitude greater than even the best nuclear thermal designs, making a trip to Jupiter a matter of months and bringing the outer solar system firmly within our reach. Researchers are exploring different methods to achieve this, from magnetic confinement that holds the plasma in a stable, donut-shaped ring, to inertial confinement where powerful lasers blast tiny fuel pellets, creating a series of miniature, controlled thermonuclear explosions. The fundamental challenge is the same one we face on Earth, achieving a stable fusion reaction that produces more energy than it consumes, all packaged into a system compact and reliable enough for spaceflight. A working fusion rocket would not just be an improvement, it would be a revolution, transforming our celestial neighborhood from a realm of distant monuments into a connected archipelago of worlds. This ambition to create a contained star leads logically to a concept of far greater and far more controversial power. Yet even the raw power of fusion pales before the sheer efficiency promised by a reactor's most fundamental particles. Fission fragment rockets take the very idea of a nuclear engine and turn it inside out, instead of using the reactor as a furnace to heat a separate propellant like hydrogen. This concept harvests the fission fragments themselves for thrust. Inside a conventional nuclear reactor, a uranium atom splits, releasing energy and creating two smaller, incredibly energetic fragments. These fragments are the shattered pieces of the atom, and they fly apart at velocities reaching 3% of the speed of light right from the moment of creation. A traditional reactor simply lets these fragments slam into the surrounding material, where their immense kinetic energy is wasted as heat. But a fission fragment rocket is designed to be almost transparent to these particles. It would use intricate magnetic fields to capture these high-speed fragments as they are born, funneling them directly into an exhaust stream. The result is an exhaust velocity that is orders of magnitude higher than any system that relies on heating a propellant. The specific impulse could reach staggering figures in the tens of thousands of seconds, making a journey to the outer planets a matter of weeks. The engineering, however, is a monumental challenge. You must maintain a critical nuclear fission reaction in a configuration where the precious fragments can escape without destroying the reactor structure itself. It requires a level of material science and magnetic control we have not yet mastered, essentially creating a leaky star in a magnetic bottle. This represents the absolute pinnacle of what is theoretically possible with fission, extracting every last drop of performance from the atom by using its very substance as fuel. Such an extreme manipulation of matter and energy hints at a possibility even more profound, a propulsion system that requires no fuel whatsoever. The ultimate engine would not carry its fuel, but harvest it from the void itself. This is the radical promise of the vacuum-to-antimatter rocket Interstellar Explorer system, or VERIES. It proposes a starship that acts as both a miner and a refiner, drawing its power not from tanks of hydrogen or pellets of uranium, but from the seething, energetic nature of empty space. According to quantum field theory, the vacuum is not truly empty. It is a turbulent sea where pairs of virtual particles, matter and antimatter, spontaneously flicker into existence for an immeasurably brief moment before annihilating each other and vanishing back into the void. The VERIES concept dares to ask a profound question. What if we could intervene in this process, using a staggering amount of energy, perhaps from an onboard fusion reactor? The ship would use powerful electromagnetic fields to rip these virtual pairs apart the instant they appear, preventing their mutual destruction. It would then funnel the collected particles into separate magnetic bottles, stockpiling precious antimatter to feed its own annihilation engine. This creates a perfect closed loop. The ship fuels itself by consuming the very fabric of spacetime, turning nothing into something with breathtaking alchemy. It is the pinnacle of self-sufficiency, a vessel that could travel for eons without ever needing to refuel. Yet this vision rests upon technologies that border on magic from our current perspective. We have no method to efficiently extract virtual particles on a useful scale, and the energy required to do so is currently unimaginable. Veris represents a theoretical endgame, a reminder that the greatest leaps may come not from building better rockets, but from learning to command the underlying energy of reality. This ambition to manipulate fundamental forces leads us to a concept that seeks to command the most familiar and most mysterious force of all. Sometimes the most powerful engine is not one you build, but one you find. Orbiting giants like Jupiter or skimming close to the Sun, a spacecraft can steal a fraction of a planet's orbital momentum in a maneuver known as a gravity assist. The planet's immense gravity whips the spacecraft around, flinging it away at a significantly higher speed than it arrived with, as if it were a stone launched from an invisible sling. This is not science fiction, it is standard practice. The Voyager probes used a grand tour of the outer planets to gain enough velocity to leave our solar system entirely, a testament to celestial mechanics as a propulsion source. In a similar vein of elegant simplicity, the solar sail harnesses the gentle, ceaseless push of sunlight itself. A vast mirrored sheet, incredibly thin and lightweight, captures the momentum of countless photons streaming from the sun. Each individual push is minuscule, but over months and years in the frictionless void of space, this accumulation of tiny kicks builds into significant velocity. It is a form of propulsion that demands patience, a slow, graceful acceleration that requires no fuel and can, in theory, carry a probe on an endless journey. These methods reveal a profound truth about interstellar travel. Raw power is not the only path. Cleverness, trajectory planning, and a willingness to use the natural forces of the cosmos itself can be just as vital as a roaring engine. This philosophy of working with the universe, however, stands in stark contrast to an ambition of sheer, monumental scale. Our next concept does not seek to use a natural planet for a boost, but proposes building an artificial one entirely for the purpose of launch. The dream of sailing to the stars is anchored to a single, stubborn problem: the crushing cost and complexity of simply leaving our own planet. Every liter of fuel, every bolt and sensor, must be blasted through Earth's thick atmosphere and powerful gravity well atop a controlled explosion. This process is so expensive and inefficient that it shackles our ambitions before they can even begin. To build the interstellar arcs we have imagined, we first need a highway to the sky. The space elevator is one such vision of a permanent, peaceful passage into orbit. Picture a cable of incredible strength, anchored at the Earth's equator and extending tens of thousands of kilometers upward to a counterweight in geostationary orbit. Along this celestial ribbon, robotic climbers would ascend, carrying payloads and people at a fraction of the cost of a rocket launch. There would be no roar of engines, only the quiet hum of machinery steadily climbing a tether to the stars. The magic and the immense challenge lies in the cable itself. It would need to be constructed from a material with unparalleled strength-to-weight ratio, something like carbon nanotubes, a substance we are only just learning to create in laboratory quantities. Without this material miracle, the entire structure would collapse under its own weight. A similar, though less towering, concept is the launch loop. This system envisions a continuously moving cable, or rotor, hurtling through a vacuum-sealed tube that is held aloft by magnetic levitation. A spacecraft would be magnetically coupled to this hypersonic ribbon and then released at the apex of its arc, flung into space like a stone from a sling. Both ideas share the same revolutionary goal: to turn the act of reaching orbit from a spectacular, fuel-guzzling event into a routine, almost mundane logistical operation. They are not the starships themselves, but the dry docks and shipyards that would make them possible. By solving the first and most fundamental step of the journey, these concepts provide the essential infrastructure for a civilization no longer confined to its cradle. With a reliable passage beyond our atmosphere secured, we can finally turn our attention to a form of propulsion that challenges our most basic understanding of physics itself. The promise of a reactionless drive, an engine that pushes without pushing anything away, is a siren song in the physics of propulsion. It whispers the ultimate shortcut, a way to bypass the fundamental need for propellant. This was the controversial claim behind devices like the M drive and the Canny drive. The concept was deceptively simple: a sealed, asymmetrical metal chamber, a resonant cavity. When filled with bouncing microwaves, the inventors claimed the radiation's pressure on the chamber walls would somehow create a net directional thrust. No exhaust, no fuel, just a gentle, persistent push from nothing. It was a claim that seemed to blatantly violate Newton's third law, the conservation of momentum, a cornerstone of physics which states that for every action there must be an equal and opposite reaction. The idea ignited a firestorm of debate, capturing the public imagination and sparking years of testing in labs around the world. The possibility was simply too alluring to ignore. Could we really get something for nothing? The long and meticulous process of scientific scrutiny, however, slowly unraveled the mystery. More rigorous and carefully controlled experiments consistently pointed to a more mundane explanation. The tiny, almost imperceptible thrust that was measured was likely not a new physics, but an old foe, experimental error. It was attributed to subtle thermal effects, the expansion of the device from heat, or magnetic interactions with the Earth's field that were not fully accounted for. While the dream of a reactionless drive captivated many, the mainstream scientific community now largely views it as a closed case, a powerful lesson in the importance of skepticism and reproducible results. The story of the M drive is not one of failure, but a vital chapter in the scientific method itself, a cautionary tale about the seductive line between a world-changing discovery and a stubborn measurement artifact. It reminds us that the universe rarely gives up its secrets for free, and that the true path forward often lies not in breaking the laws of physics, but in understanding them more deeply than ever before. This return to established physical law brings us to a concept that embraces one of the most extreme environments in the cosmos. Yet the brilliance of the laser sail reveals its most profound weakness. It is a vessel built for a one-way trip, capable of reaching phenomenal velocities with no way to slow down. A probe accelerated to 20% of light speed would flash past its target star system in a matter of hours, a helpless blur of data with no chance for a detailed survey. The very emptiness that allowed its acceleration now denies it a destination. This problem of interstellar braking demands a solution as elegant as the sail itself, one that finds a way to create drag where there is almost nothing to push against. The magnetic sail, or mag sail, is that ingenious answer. It proposes turning the void itself into a brake pad. Imagine a spacecraft unfurling a vast, superconducting loop, a hoop of wire that could be dozens of kilometers across. When an electric current is sent through this loop, it generates an immense, expansive magnetic field, a kind of invisible magnetic parachute. This field does not interact with solid matter, but with the sparse, ionized hydrogen atoms that drift through the interstellar medium. As the ship plows through this tenuous gas at relativistic speeds, these charged particles are deflected by the magnetic field, transferring their momentum to the spacecraft and gradually slowing it down. Each tiny interaction is a minuscule tug on the cosmic brakes, but over years of travel, this constant, passive drag can bleed away enough velocity to allow the craft to be captured by the destination star's gravity. The magsail transforms the greatest challenge of interstellar space, its incredible emptiness, into the very mechanism needed for arrival. It is the essential counterpart to any beamed propulsion system, the missing piece that turns a high-speed fly-by into a mission of true exploration. This ability to slow down without fuel underscores a deeper truth about the journey to the stars, that the destination is just as important as the speed of the voyage. The promise of fusion finds its ultimate expression not in raw power alone, but in the elegance of a cleaner, more direct reaction. While standard fusion combines deuterium and tritium, that process unleashes a torrent of high-energy neutrons, a form of radiation that is incredibly difficult to contain and that bombards the ship's structure, making it radioactive over time. The helium-3 fusion rocket proposes a different path. It fuses deuterium with a light, rare isotope of helium that has only one neutron instead of two. This specific reaction primarily yields charged protons and a helium nucleus, particles that can be guided and controlled. Instead of a spray of unstoppable neutrons, the engine produces a focused stream of charged particles, which magnetic nozzles can then direct with surgical precision to generate thrust. This means more of the fusion energy is converted directly into propulsion, resulting in a far more efficient engine with drastically reduced radiation challenges for the crew and the spacecraft's electronics. It is the difference between trying to harness the blast wave of a bomb and the precise beam of a laser. The fuel itself, however, is the key to the puzzle. Helium-3 is incredibly scarce on Earth, but it is thought to be abundant elsewhere in our solar system. The lunar surface, bombarded by solar winds for billions of years, is believed to have vast reserves trapped within its dusty regolith. The atmospheres of gas giants like Jupiter and Saturn are another potential treasure trove, containing volumes of this precious isotope beyond our imagination. This creates a breathtaking vision of a future economy in space. The quest for helium-3 could ignite a solar system-wide mining industry, with robotic harvesters scouring the moon and massive gas scoopers diving into the upper atmospheres of distant planets. This is not just about building a faster rocket, it is about building the fuel depots that will support an entire fleet of them, turning the solar system into a network of cosmic filling stations for the starships of tomorrow. This ambition to draw fuel directly from our celestial environment mirrors a propulsion concept that takes its inspiration not from industry, but from the living world itself. While most rocket engines roar, these whisper. Electric propulsion is the silent, steady pulse of modern space exploration, already at work in the void around us. These are not engines of explosive force, but of patient, relentless acceleration. The principle is one of elegant efficiency. A neutral gas, typically xenon, is injected into a chamber where its atoms are stripped of their electrons, creating a soup of charged particles called a plasma. This ionized cloud is then gripped and hurled outward at phenomenal speeds by powerful electric fields, generating thrust. The individual push from each ion is minuscule, a force often compared to the weight of a single sheet of paper resting on your hand. Yet in the frictionless environment of space, where there is no air resistance to overcome, this gentle nudge never stops. Over weeks, months, and years, this continuous pressure accumulates, allowing a spacecraft to build up velocities that would be impossible for a chemical rocket carrying the same mass of fuel. This is the magic of specific impulse, a measure of fuel efficiency. Electric thrusters achieve specific impulses that are an order of magnitude greater than their chemical cousins. making them the undisputed champions for long-duration missions. We have seen their incredible capability in action. The Dawn spacecraft used its ion thrusters to perform an unprecedented orbital tour, maneuvering into orbit around the asteroid Vesta and then leaving to orbit the dwarf planet Ceres, a feat that would have been unthinkable with conventional propulsion. These systems are the quiet workhorses, the tugs that patiently shift satellites into precise orbits and guide deep space probes on their multi-year journeys. The future points toward even more powerful electric engines, like magnetoplasmadynamic thrusters, which use magnetic and electric fields to accelerate plasma to even higher energies. These could one day propel heavy cargo ships on slow, efficient spirals across the solar system, serving as the freight trains for an interplanetary supply chain or providing station keeping for vast generation ships. They represent a philosophy of motion built not on brief, fiery power, but on the unwavering certainty of a constant, gentle push. This established, almost serene technology could not be more different from a concept that draws its power from the most chaotic and energetic events in the universe. There is a certain audacity in harnessing the most destructive force in the cosmos as your engine. This is the radical premise of the black hole Starship, a concept where the ultimate power source is not a star in a bottle, but a singularity in a box. Physicist Louis Crane proposed a vessel that would carry an artificial micro-black hole with a mass of around 1 million tons. Such an object would be smaller than a proton, yet it would possess a ferocious appetite, constantly evaporating by emitting Hawking radiation. This stream of particles and energy, with an output equivalent to 1,000 large nuclear power plants, would be the ship's fuel. This radiation could be focused by a parabolic reflector to create thrust, like a photon rocket of unimaginable efficiency, or used to generate electricity for an onboard power grid. To prevent the black hole from evaporating completely, the ship would need to constantly feed it with matter, likely collected from the interstellar medium or an onboard supply, carefully balancing consumption against decay. The engineering, however, descends into the realm of the nearly divine. Creating such a micro-black hole in the first place is a challenge that may require a particle accelerator encircling the entire sun, a project for a civilization that has already mastered its solar system. And then you must contain it. This infinitesimal point of infinite density would need to be held in a perfect magnetic trap, for if it ever drifted toward the walls of its chamber, it would instantly begin consuming the ship itself. This is not merely a propulsion system, it is an act of cosmic taming, a declaration that even the laws of the event horizon can be bent to the will of a traveling intelligence. It pushes the limits of what we can even conceive, imagining a future where we do not merely avoid the universe's most terrifying phenomena, but recruit them as our steeds. This profound manipulation of fundamental forces finds a strange parallel in a concept that seeks to rearrange the very particles of space itself. The Q-thruster concept dares to question a force so fundamental we barely notice it, inertia itself. It asks why objects at rest tend to stay at rest, and why moving objects resist a change in their speed or direction. Physicist Mike McCulloch's theory of quantized inertia offers a radical answer, one that ties the local behavior of an object to the vast, accelerating expansion of the entire cosmos. The theory suggests that inertia is not an innate property of matter, but a kind of pressure, a result of an object interacting with a sea of radiation generated by its own acceleration relative to the cosmic horizon. This is Unruh radiation, a theoretical glow that only an accelerating object would perceive. In this view, an object resists being pushed because it is, in a sense, pushing against the entire universe. A Q thruster is the proposed engine that attempts to manipulate this effect. It consists of a metal cavity tapered like a cone in which microwaves are bounced back and forth. According to the theory, the unique shape and the resonant microwaves create an asymmetry in this UNRWA radiation field, resulting in a net force, a gentle push from within the cavity itself. No propellant is ejected, no fuel is burned. It is, in essence, an attempt to create thrust by persuading the quantum vacuum to push back unevenly. The parallels to the M drive are obvious, and the skepticism from the broader physics community is equally intense. The central challenge is that quantized inertia remains a highly speculative framework, not yet integrated into the established models of physics. Reproducing the experimental results has proven difficult, with many scientists attributing the tiny measured forces to subtle thermal or magnetic effects. Yet the persistence of such ideas highlights a thrilling and sometimes frustrating reality at the edges of science. They represent a deep and enduring hope that we might find a crack in the armor of known physics, a loophole that could one day open the cosmos. These concepts live in a space of tantalizing possibility, reminding us that our maps of reality are still being drawn, and that the next great discovery might lie just beyond the edge of the page. This search for a cosmic shortcut now leads us to a concept that does not try to find a crack in physics, but to build a permanent tunnel through it. A true interstellar highway would not be a ship, but a tunnel carved through the fabric of reality itself. The Krasnikov tube is this very idea, a thought experiment that reimagines travel not as a voyage through space, but as a commute through a permanent cosmic subway. The concept begins with a one-way mission. An advanced civilization would dispatch a vessel to a distant star, traveling at near light speed. But this ship would do more than just travel. It would actively modify the spacetime along its entire route, warping and compressing it to create a permanent, stabilized tube. Upon arriving at the destination, the crew would then activate a similar process on the return leg, completing the infrastructure. Once this colossal engineering project is finished, the tube becomes a static feature of the universe, a fixed road connecting 2 points. The magic happens on the journey home. A second ship entering this pre-established tube would not experience the vast distances of normal space. From the perspective of its crew, the trip could be almost instantaneous, a brief transit through a shortcut in the cosmos. It is crucial to understand that this does not permit time travel into the past. It simply redefines the distance between 2 points for anyone using the highway. Unlike the Alcubierre drive, which is a dynamic engine moving a bubble of space-time, the Krasnikov tube is permanent infrastructure. It represents a fundamental shift in philosophy, from the ambition of building faster cars to the profound undertaking of laying down the interstate itself. This is the work of a truly mature stellar civilization, one that thinks not in terms of single missions, but in millennia-long projects to reshape the galaxy for generations to come. Such a civilization would need power on an inconceivable scale, drawing energy not from portable fuel, but from the nearest and most reliable star. 19th on our list is a propulsion system that finds its power not in a reactor core, but in a simple, elegant mirror. The solar thermal rocket is a brilliant exercise in working with what the universe readily provides. Picture a spacecraft equipped with vast parabolic mirrors, like those in a giant solar power plant, but unfurled in the vacuum of space. These mirrors concentrate raw, unfiltered sunlight onto a central heat exchanger, a chamber that glows with the focused intensity of a small star. A propellant, typically liquid hydrogen, is pumped through this superheated core. In an instant, the frigid gas is blasted into an incandescent plasma, expanding violently and roaring out of a nozzle to generate thrust. The principle is identical to a nuclear thermal rocket, but it swaps the complex atomic heart for the clean, predictable fury of the Sun. Its performance is modest compared to its nuclear cousin, with a specific impulse likely under 1,000 seconds, but its advantages are profound. Sunlight is free, limitless, and requires no political approvals or complex safety protocols. There are no radioactive materials to contain, no dangerous fuels to synthesize. This makes the solar thermal rocket an ideal candidate for a sustainable transportation network within the inner solar system. Tugs powered by sunlight could ferry cargo between Earth, Mars, and the asteroid belt, their mirrored sails harvesting power from the very star they orbit. It is a testament to practical ingenuity, a reminder that the next great leap might not always require the most powerful technology, but the most clever application of the tools already at our disposal. This elegant, almost serene technology stands in stark contrast to the concept that follows, a system born not from celestial mirrors, but from the chaotic heart of a star itself. Sometimes the most practical path forward is not a single solution, but a clever fusion of two. The hydrogen-ingesting ramjet embodies this hybrid philosophy, offering a strategic compromise between the dream of a fuel-gathering starship and the hard reality of physics. Also known as the Ram-augmented interstellar rocket, or RAIR, this concept does not abandon the fuel tank entirely. Instead, it carries a precious, dense supply of a potent fusion fuel like deuterium. But it also unfurls a magnetic scoop, just like its Bussard cousin, to harvest the sparse hydrogen atoms drifting through the void. The true ingenuity lies in how these two sources are combined. The ship uses its onboard deuterium as the primary energy source, the spark plug for its fusion reactor. The scooped hydrogen, however, is not used as a primary fuel, but as reaction mass. It is the material that gets superheated and violently ejected out the engine nozzle to create thrust. Think of it as the difference between a car that carries its own gasoline, but also collects rainwater to spray onto its superheated engine, creating a massive burst of steam for extra power. This deuterium-hydrogen fusion process is far more feasible than the sluggish proton-proton fusion a pure ramjet would require. It sidesteps one of the Bussard concept's greatest hurdles. The collected hydrogen acts as a propellant multiplier, dramatically stretching the usefulness of the finite deuterium supply. This allows the spacecraft to accelerate for much longer and achieve a far greater final velocity than a conventional fusion rocket carrying the same initial mass. It represents a middle road in interstellar engineering, blending the assured power of carried fuel with the expansive efficiency of harvesting from the cosmos. This elegant compromise acknowledges that the universe may not provide a perfect fuel source, but it can still offer a generous helping hand to those clever enough to accept it. Such a hybrid model, balancing what we bring with what we find, leads us to a propulsion concept based on one of physics' most profound and enduring mysteries. The universe holds its greatest secret in plain sight, a ghost that permeates every corner of space yet remains utterly invisible to our finest instruments. Dark matter exerts a gravitational pull that guides the rotation of galaxies, a cosmic scaffolding that holds the structure of reality together, yet we have no idea what it actually is. This profound mystery is the foundation for one of the most speculative propulsion concepts ever conceived, the dark matter drive. Imagine if we could not only detect this elusive substance but command it. One theoretical idea suggests a spacecraft could be designed to emit streams of dark matter particles, creating a novel form of thrust as these exotic particles stream away from the ship. An even more ambitious proposal envisions a vessel that interacts directly with the vast, swirling halo of dark matter that envelops our entire galaxy. Just as a sailboat tacks against the wind, such a ship might somehow harness this invisible current for propulsion or lift, riding a river we cannot see through the void. This concept exists entirely in the domain of imagination, a sketch for an engine that cannot be designed until we first answer the most basic questions about its fuel. It serves as a powerful reminder that our greatest leaps into the cosmos may not begin in an engineering lab, but at a particle detector with a fundamental discovery that rewrites the rules of physics itself. This journey into the deepest unknowns of the cosmos brings us back to a technology with a very tangible and very volatile source of power. The ultimate chemical fuel may not be a complex molecule, but the universe's most basic element transformed into a new state of matter. Metallic hydrogen rockets are built on a stunning theoretical possibility that under pressures exceeding those found at Earth's core, the simple hydrogen gas that fills stars can be crushed into a shimmering, solid metal. This substance is predicted to be metastable, meaning it could remain in its metallic form even after the crushing pressure is removed, like a diamond forged from carbon. If this proves true, its potential is staggering. As a rocket fuel, metallic hydrogen's specific impulse could reach into the thousands of seconds, a performance an order of magnitude greater than the most advanced chemical propellants we use today. A spacecraft powered by this material could reach Mars in weeks or make round trips to Jupiter's moons feasible, completely revolutionizing travel within our solar system. The energy density locked within its atomic lattice is so profound that it would render every other chemical rocket instantly obsolete, acting as the ultimate bridge technology, a chemical springboard to the nuclear age. Beyond propulsion, metallic hydrogen is theorized to be a superconductor at room temperature, a material that could revolutionize power transmission and magnetic levitation on a global scale. Yet for all its promise, this substance remains the holy grail of high-pressure physics. Claims of its creation in laboratories have been fiercely debated, with the tiny samples proving incredibly difficult to sustain and study before they seemingly vanish. The challenge is not just achieving the monumental pressure required, but also finding a way to trap and stabilize the material long enough to be utilized. It is a ghost of a fuel, a theoretical powerhouse that continues to defy our attempts to capture it. This pursuit of extreme states of matter, where the very rules of chemistry are rewritten, leads us to a concept that challenges the most fundamental rule of motion itself. The very atoms of a ship could become its engine if a subtle quirk of physics proves real. The Mach effect thruster proposes that an object's mass is not a constant, unwavering property, but something that can momentarily flicker. According to physicist James Woodward's theory, when an object accelerates through the cosmos, its mass experiences tiny, transient fluctuations, a direct consequence of its interaction with the entire universe, a concept rooted in Mach's principle. The thruster itself is a remarkably simple device in principle. It uses a piezoelectric crystal, a material that vibrates when you apply an oscillating electrical voltage. The theory suggests that if you pulse this voltage at the precise moments the crystal is accelerating and decelerating, you can harness those fleeting instants where its mass is theoretically heavier or lighter. By carefully timing these pulses, you could, in theory, generate a tiny but continuous net force, a push that comes from within the device itself without any exhaust or propellant. It is the ultimate dream of a self-contained engine. Like its cousins, the Q thruster and the M drive, the Mach effect thruster exists in a contentious space. A small, dedicated community of experimenters has reported measuring minute amounts of thrust in laboratory tests, results that defy easy explanation by conventional physics. Yet these findings remain deeply controversial. as they have not been widely or consistently replicated by the broader scientific community. The measured forces are so incredibly small that they sit on the very edge of what our instruments can detect, leaving open the possibility of unseen experimental errors or subtle thermal effects mimicking a thrust signal. This ongoing pursuit represents a profound human endeavor, the relentless search for a loophole in the universe's operating manual, a way to coax motion from the fabric of reality itself. While these concepts challenge physics on the smallest of scales, our final leap demands a canvas of almost inconceivable size. The final frontier may not be conquered by speed, but by endurance. When velocity is a barrier we cannot break, the solution is to transform the journey itself into a destination. This is the profound philosophy of the interstellar arc, a vessel not built for a single mission but for countless lifetimes. Often called a world ship, this would be the largest structure ever conceived by humanity, a mobile planetoid carrying an entire civilization on a voyage lasting thousands of years. Its propulsion is almost secondary, a slow, steady, and supremely reliable system like fusion or nuclear pulse that burns for centuries, a gentle nudge across the cosmic ocean. The true engineering marvel is not the engine, but the arc's closed-loop biosphere. Imagine vast, rotating cylinders simulating Earth's gravity, filled with forests, farms, and freshwater seas, all meticulously balanced to recycle every molecule of air, water, and waste. This self-contained world must be perfectly stable, a delicate bubble of life hurtling through the void, immune to the slow decay of time and the absolute silence outside its hull. The greatest challenges, however, are not technological but human. How does a society maintain its purpose and identity when the launch planet is a forgotten myth and the destination is a legend for unborn generations? The crew born en route would know no other home. Their culture, their history, their very sense of reality would be defined by the ship's endless corridors and the star maps on their screens. The social and psychological resilience required for such an endeavor is beyond anything we have ever attempted. This concept forces us to ask what it truly means to be a spacefaring species, not just as explorers, but as a civilization that can pack its entire world and carry its future into the night. It is the ultimate act of patience, a promise made to our descendants that the journey, no matter how long, is worth the world we bring with us. The ultimate destination in our journey through propulsion is not an engine at all, but a tunnel. A wormhole, or Einstein-Rosen bridge, is a hypothetical shortcut through the folded fabric of spacetime itself. Picture the universe not as a flat sheet, but as a crumpled piece of paper. Two distant points on the surface could be brought nearly together by a bridge passing through the higher dimension. A traversable wormhole would be that bridge, a cosmic subway connecting 2 points that might otherwise be separated by thousands of light years. The journey through the throat could be instantaneous, rendering the very idea of distance meaningless. This is not about moving faster, but about choosing not to make the trip at all. The mathematics of Einstein's general relativity permit such structures, but the physical requirements are staggering. To prevent the tunnel from collapsing into a singularity the instant it forms, you would need to line its throat with exotic matter, the same theoretical substance with negative energy density required by the Alcubierre drive. This material would act as a kind of anti-gravity, propping the cosmic doorway open against the relentless crush of its own gravity. Whether such matter can exist in useful quantities is one of physics' great unanswered questions. Finding or creating a stable, macroscopic wormhole remains a dream for a civilization with power over the cosmos itself, the final frontier of travel where we would not conquer space, but delete it from the equation entirely. Having journeyed from the controlled fury of nuclear engines to the serene geometry of spacetime tunnels, a common thread emerges from all 25 concepts. They are not merely a list of technologies, but a map of human ambition itself. Each one represents a different answer to a single, profound question. Will we force our way across the void with raw power? Will we cleverly harvest energy from the cosmos around us? Or will we find a way to rewrite the rules of the game entirely? These 25 paths forward are not a chaotic list, but a grand symphony of human ingenuity, each playing a distinct part in a shared melody. They harmonize around a few powerful themes: a relentless drive toward greater exhaust velocity, a clever dance around the tyranny of the rocket equation, and an audacious desire to command the very fabric of spacetime. We see a clear progression from the near future, where nuclear thermal rockets could become the workhorses of our solar system, to the distant horizon, where the physics of warp drives and wormholes remain a beautiful, tantalizing mystery. The true journey to the stars will not be a single silver bullet solution. It will be a layered strategy, a tapestry woven from many threads. We might dispatch fleets of tiny, laser-propelled probes as our scouts, their one-way journeys illuminating the darkness ahead. Slower, more massive fusion arcs could follow, carrying generations of explorers on voyages of centuries. And all the while, in laboratories here on Earth and in orbit, we must continue the fundamental research into quantum gravity and negative energy, nurturing the seeds of concepts that may one day allow our descendants to skip the journey altogether. This synthesis reveals that interstellar travel is not one single problem to be solved, but a sprawling ecosystem of challenges, each demanding its own breakthrough in physics, engineering, and social science. It forces us to look beyond the blueprints and equations to ask a more profound question about ourselves. What does it mean for a species to decide that its future lies not on a single world, but scattered across the light years, carried by the very engines we are only now beginning to dream into existence? These 25 pathways to the stars are far more than a catalogue of scientific speculation. They are the vital beacons illuminating the future of our entire species. Each concept, from the brute force of antimatter to the serene geometry of wormholes, represents a fundamental facet of our nature. It is our innate desire to explore, to push against every boundary, and to secure our long-term survival by planting our civilization among many suns. The challenges we have discussed are indeed monumental, demanding breakthroughs in physics and engineering that currently border on magic. Yet the very act of contemplating such profound ideas, of daring to calculate the energy needs of a warp drive or the social structure of a world ship, actively expands the realm of what we believe is possible. It stretches our imagination and forces our science to catch up. The astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. Our journey to uncover these incredible things does not begin with the roar of a rocket engine. It ignites with a single, quiet spark in the mind, a question, a calculation, a what-if scribbled on a notepad. Let this exploration be a catalyst for your own curiosity. For the dream we nurture today, the concept we debate and refine, may one day become the vessel that carries our descendants to worlds we can only dream of from our pale blue dot. The future of propulsion is not a distant story. It is a narrative being written in laboratories and universities at this very moment, and that leads to the most exciting question of all. What role will you play in writing the next chapter? We would love to hear which of these incredible concepts captures your imagination the most. Share your thoughts in the comments below, and if you want to continue this journey to the final frontier, be sure to subscribe.